Hi.
Hello, this is Mr. Bergman.
Guess what we forgot today?
We forgot the tripod!
Yeah.
So Mr. Sam's is holding the camera, making you sick to your stomach. And now I'm upside down and now upside right. And oh, Mr. Sam's, that is just way scary.
Yeah, I need a shake.
You know what we're going to talk about today, Mr. Sam's?
Yeah, what's that?
Vapor pressure.
Oh, yeah.
You know, vapor pressure is kind of like pressure. So
Yep.
like when I take your head and I squish it, and I hurt him, you see,
Yeah.
and that's vapor pressure. But actually, that's just pressure. We want to talk about, that's painful. Oh, Lord have mercy. Do you want to look at his eyeball? What color are his eyes? You can see very clearly. I think we're going to start the podcast. What do you think?
Okay.
All right. So today we're going to start talking about solutions, phase diagrams, etc. Chapters 10 and 11. And actually, if you read on, we'll do 21 and 22 too. This is a
Actually,
whole
21 and 18.
No, it's 22.
No,
yeah,
it's
in the
18.
new book. In the old book, it was 18. I'm pretty sure. Oh, yeah, I'm right. I'm always right. Yeah, we'll check. I'll prove it to you.
No, I'll prove it to you. I just made all the answer podcasts.
I know, but you were wrong. Okay. All right. Hey, so today we're just going to tie up Chapter 10.
You know what it is? It's 22 and 18. 22 is organic, and 18 is
20.
nuke.
Oh, I think you're right, actually.
Yep.
Yeah, you're
We're
right.
both wrong.
I think we're both wrong.
Yep.
You're right. Oh, today, vaporization. Hey,
All right.
what the heck is vaporization?
Well, vaporization is when we're going from the liquid
I can do that.
to the gas phase
Gas. Yeah, okay. But
at its boiling point.
at its boiling point.
Yeah.
Okay. Now, like, water boils at 100 degrees, right?
If we live at sea level, yeah.
But, like, other things, they boil at 100. Everything boils at 100, right?
No, just water.
Just water? So other things can boil at different temperatures?
Uh-huh.
Okay, that's important to know, guys.
And very important. Don't get stuck on 100 unless you're dealing with water.
And that only applies at sea level, even for water.
Yep.
So that's different. Okay, evaporation's kind of a little different.
Yeah, we're
ballgame.
still going from a liquid to a gas.
Okay, liquid, I can do that, to gas.
But this occurs at when we're below the boiling point.
Okay, so, and you guys know that. If you take a beaker of water and you leave it out overnight, it will evaporate.
Yep.
Evaporates pretty quickly where we live because we live in a dry climate. But if you were in a more moist climate, it would evaporate more slowly.
Yes.
More slowly?
Slowerly.
Yeah, something like that. Hey, and boiling is even kind of a different thing. That's, of course, a liquid to a gas. Mm-hmm. Huh.
Yep, and that happens when the vapor pressure
That's when
is
the vapor pressure.
equal to the atmospheric pressure.
So, folks, there's two ways to boil a liquid. Liquid. We're having a hard time talking today. So.
Yes, yeah.
If you lower the pressure, you can boil a liquid.
Yep.
So, Mr. Sams, if you were like step outside
Uh-huh.
from the space shuttle, let's say you got one of those teachers in space things,
Yeah.
and you said, I'm going to go outside the space shuttle,
Oops, I forgot my suit.
and you decided to jump out there because you forgot your wrench out there.
Yep.
While
My
you
bag
were
of tools
your
was
bag of
floating
tools.
away. My $150,000 bag of tools.
So you said, I'm just going to hold my breath. I'm pretty good at holding
Yeah,
my
yeah.
breath. What's going to happen?
I'm gonna boil.
Yeah, your blood would boil. So that would not be because you see the pressure outside in space.
Very, very low, almost zero.
So yeah, his blood would boil and he would die a painful death. So yeah, so vapor pressure. Here's essentially a cool picture of vapor pressure. You can see that these are molecules, and of course they are evaporating, and some of them are just floating around in the flask, right?
Yep.
And it exerts a particular amount of pressure.
Yes, particular meaning it's measurable and predictable.
It's an amount,
Yes.
yeah.
And at different temperatures, it's a different pressure.
Yeah, the pressure varies with the temperature. There's actually curves, and we'll show that in just a second. Oh, we need a microphone, Mr. Sams. I bet it'd be better if they could hear me. So, folks, I'm here with you live. Well, I'll record it with a vat of boiling water. Boil, boil, boil. The atmospheric pressure is equal to the
Vapor pressure.
vapor pressure, and you can actually see the vapor coming off. You see the steam right here. I don't know if I were to kind of put a blue background on this. Is that easier to see, Mr. Sams?
Probably, yeah.
Can you see the steam better now? Maybe not?
Yeah, a little bit.
Well, you can see the steam coming off. And so the liquid is turning from a, liquid to a gas. And it exerts a pressure. Now, to illustrate the pressure, I happen to have a stopper right here. I'm going to place the stopper in the flask, and we're going to see what happens.
I have a feeling I should have safety glasses on.
Yeah, I have safety glasses on.
I'm behind
And
the
so I'm
camera.
going to put, ouch, that's very hot.
Yeah, don't touch that.
Yeah, okay.
What'd you learn from that?
All right. So watch what happens. Probably need a better seal.
Oh!
There we go. So it pops the top. It sometimes can be more explosive than that, but of course what was causing that was the extra molecules of gas that were in the vapor state, and they caused the top to pop off.
Do it again. Do it again.
All right, again. A little better seal and not try and burn.
Now that I have my safety glasses on.
Ah, that really is hot.
It's boiling hot.
All right, so Mr. Bergman is going to stand back here. The pressure
Did you get it too hot,
extinguisher.
did you? Too hot?
I hope not. It could get very interesting.
Shatter into a million.
Shattering into a million. Oh,
there it
there we
goes.
go. Okay, so we make a little explosion.
Yeehaw.
So, very simple. Vapor, liquid goes from to a gas, and we now have discovered the concept of vapor pressure, and that we can actually use vapor pressure to knock a stopper off the top. And so you can see the concept of vapor pressure, and that was at a higher temperature. And so I bet we could make a judgment here. What do you think about vapor pressure and temperature?
Temperature goes up, vapor pressure goes up.
So if temperature goes up, then the vapor pressure goes up. All right? All right. Now, we could actually call this, when it's boiling, something called the heat of vaporization or the enthalpy of vaporization. This actually is a number. So if I were trying to measure how much heat it takes to boil a particular liquid, it's called the heat of vaporization. It's the delta H of vape. Okay? And for water, which we were just watching boil just a minute ago, I believe it's 2.26 joules per...
Oh boy, I don't remember the number.
Not that
I'll look
important.
it up.
Yeah, not that important what that is. Okay. Now we should also then talk about condensation. All right. What is condensation? We have a little typo here, it looks like. But condensation is when you have a gas turn into a liquid. All right. Now we have a situation where we can have what's called equilibrium. All right. So what we've got going on here, folks, is let's say that I have a flask, and actually draw this picture, and we'll show it in real life in just a second. And you've got a liquid right here, and it's a sealed system, so you put a stopper in there or whatever, right? And so some of that liquid, that's liquid, some of that liquid is evaporating, isn't it? Mm-hmm. But then also some of it is condensing. So if it's at a particular set temperature, you have both condensation and evaporation taking place. This is called the equilibrium vapor pressure, or sometimes this is called a dynamic equilibrium.
Yeah, because at that state, the same number of molecules are leaving the liquid phase and entering the gas as are leaving the gas and becoming a liquid again.
So if we go back to this picture, you can see this actually is the picture of the dynamic equilibrium. Some of them are evaporating. This molecule is evaporating, and this molecule is condensing. And this would be a system where it's at equilibrium.
Yep, there's 3 going in and 3 going out.
Yeah, so that's equilibrium. Okay? So if we want to look at this in real life, so I have the flask right here, right? The flask that we were just looking at, and I put the stopper on. I took it off the hot plate a few minutes ago. And what's happening, of course, is that some of the water is evaporating. Now you can't really see it evaporating, but it is. And then you see some condensation. Actually, if you look on the outside of the flask, you're going to see condensation. And so it's both condensing and evaporating at the same time. In fact, if you look over here, I can see a drop of water dripping down. And so this is at equilibrium. It's kind of changing to some degree because this is now cooling. You can see me using the hot glove because this is quite warm. I don't want to burn my hand. But you can get the idea. Okay? All right, so if we were to draw this in a graph, we can say that over time, as you heat something up, the rate of this line here would be evaporation, and then the rate of, pardon me, I did that wrong. This is the rate of condensation. If you're at a set temperature, the rate of evaporation is a constant. This is evaporation. But you see, once you seal it, once you seal your flask, like we did, all right, once you seal the flask, you don't have anything to condense yet, and it starts to. And eventually, they reach the point where the rate of evaporation is equal to the rate of condensation, and they become equal. So it's equilibrium. Okay? Not terribly difficult. Now, we can also talk about pressure in terms of, when we talk about this is kind of related to Dalton's law. So if I have a particular chemical, all right, this is a
Column of mercury.
Mercury barometer, thank you. And then if I then throw some water in here, if you look carefully at this picture, there's just a skosh amount of water. And the way they measure this is they put some water in there and they measure the difference. Normally this is at 760 at 1 atmosphere, but when they do this with just a skosh amount of water, it pushes the mercury down a little bit. It pushes it down.
Vapor, by the way.
Yeah, water vapor. But you do put water liquid right here, and then that water liquid evaporates. And so you got little molecules of water in your tube right here. And as they press, they're actually pressing down, and at this particular temperature, I don't know what temperature we're at, it gives you a particular pressure.
Yep.
And if you do that with a different chemical like ethanol, it gives a greater pressure, and if you use this chemical, it gives even a greater pressure. So they have different pressures. Now, something that's intriguing to understand about the different pressures, it relates to the last unit that we just talked about. It has to do with bonding. Okay, those liquids that give a high vapor pressure, like the diethyl ether, the pink one or whatever color you want to call that, would have what type of a bond, Mr. Sams? Strong or weak?
They're going to be weak bonds.
Yeah, you see the ones with high pressures, high vapor pressures have weak bonds, and those with strong bonds have low vapor pressures. Water's low because water's held together by hydrogen bonding.
Yeah.
Diethyl ether is held together by London dispersion forces, and therefore it has a very weak bond and therefore a high vapor pressure because it's easy to evaporate. If you think about it, if you want to evaporate a liquid, you got your beaker or whatever, and if it's easy to evaporate, that means it's got weak bonds. Now maybe you guys have filled the tank of your car with gasoline, and what do you notice when you're filling the tank?
When you open the cap,
yeah,
kind of go. Tss.
Yeah, that too, and also just you can smell it pretty strongly too, right? And that's because it has a high vapor pressure, and it evaporates pretty easily because it's held together by weak London dispersion forces.
Yeah, and things with high vapor pressures we call volatile liquids.
Yes, yeah. Actually, that's a good point. Somewhere, ignore this picture for just a moment. The word volatile. I-L-E. Volatile. Most people think of the word volatile to mean it burns, and that's not true. Volatile just means it evaporates easily. It means it's held together by weak bonds.
Right, which will in turn make it burn easier.
Yeah, if it is a burning chemical, but not all chemicals that are volatile are explosive, although quite a few of them are. All right. What happens in the process of evaporation? This is what we call the classical Boltzmann diagram. And basically, if I've got a T1 being a cold temperature, those molecules, because we say they actually have an average, this is the average kinetic energy, but some of them will have a very high amount of energy. These are the molecules that will evaporate. Now, if I raise the temperature, this is the same beaker, if you will, with higher temperature, I now have more molecules with enough energy to evaporate. And so at a higher temperature, it's basically the area under this curve is the higher temperature. All right?
Okay.
All right. And a graph that's kind of important to understand, we just talked about this. Of course, at higher temperatures, what happens to vapor pressures?
Goes up.
It goes up. So here's water right here. This is actually the actual vapor pressure at various temperatures. And so if I'm at 60 degrees Celsius, the vapor pressure of water looks like it's about 200 millimeters of mercury. Right here, right?
Yep.
But an interesting point that we should note here, at 760 millimeters of mercury, or the the pressure of water, or the atmospheric pressure at sea level, what's the interesting point here?
That's where the vapor pressure is equal to the atmospheric pressure.
And that would be 100 degrees.
That is the normal boiling point of water.
Yeah. Now, why did you say the normal boiling point?
Normal boiling point refers to the boiling point at 1 atmosphere, or 760 torr, or at sea level.
Correct. And you see, folks, we live, those who don't know this, we live at a pretty high altitude, 8,500 feet. And I did the pressure this morning in my class, and we live at, our pressure today was 570, something like that.
Usually sits right around 570.
570 millimeters of mercury. And so if you were to take this ball game down right here, whenever it's, this comes out to about 92 degrees Celsius. So where we live, water boils at 92 degrees
Which
Celsius.
happens to be the perfect temperature to make a perfect cup of coffee.
Oh, really?
So when you boil water up here, you can put boiling water in your coffee, and it makes the perfect cup of coffee. Normally, it has to be a little bit below boiling.
But, well, it's 92 here in Woodland Park.
And I do like my coffee.
So that's another way to look at this is how we can boil water. If I'm at the top of Mount Everest, I don't know the pressure of Mount Everest. Let's say for the sake of argument, it's 400 maybe.
It's probably lower than that.
I think it's lower than that. Whatever. Water would boil at 80 degrees, and so now you'd have actually kind of lukewarm water if you're making your coffee.
Stick your finger in your boiling water.
Yeah. Now this particular line is a curve, and guess what?
What?
It has an equation.
It does.
Mathematical
yes,
equation.
It does.
And so, in fact, if you plot a graph, this is the graph of vapor pressure versus temperature, if you wanted to draw a straight line, it will be the natural log of the vapor pressure versus 1 over the Kelvin temperature. Kind of confusing, and that gives you a straight line, and then it will have the equation y equals mx plus b. Now, but actually, y will be the natural log of the vapor pressure will be equal to the slope of your line, and the slope of your line is delta H.
VAP, heat of vaporization.
Actually, where would it be? That's actually the simplification one there. We're looking at our book, guys.
Oh, this one over here?
Yeah,
there it is.
There it is. It'll be
it's actually negative.
Of course, it's the negative slope. Negative delta H vaporization. Remember we talked about that over R. Oh, there's that R.
Yeah.
Times 1 over the temperature. That's in Kelvin plus some constant.
Yep.
Okay.
So the natural log of your vapor pressure is your Y. Your M is negative delta H over R times 1 over T. That's also part of M. And then, that's X, sorry. And then plus B is your constant there.
And that's just your constant. That's your B. Okay. I think I have it out. So, I think we've already said this, but how do you boil something up?
Either heat it up.
Heat it up.
Or lower the vapor pressure.
Lower
or the atmospheric
pressure.
Sorry.
Bloop. All right, we already did our demo. Okay, so here's the equations. Actually, I typed
look
them
at
out.
that.
How's that for a while? And actually, if you rewrite this equation when you're comparing two vapor pressures, this is the more important equation right here.
Yes.
And it has a name that I think
it's the Clausius-Clapeyron equation.
The Clausius-Clapeyron equation made by Mr. Clausius.
Yes, so we have Clausius-Clapeyron, and then we had the Henderson-Hasselbalch back when we did acids and bases. So.
Yeah. All right, so now let's do a mathematical example. So if we've got a vapor pressure of water at 25 Celsius, it's at 23.8 torr. The heat of vaporization is this number. What is the vapor pressure of water at 50 Celsius? So we're going to use this second equation. This second equation, the Clausius-Clapeyron equation, is really the more important equation. So you basically have two temperatures and two vapor pressures. So the torr, this is 25 degrees Celsius. I'm going to call that T1. 23.8 I'm going to call VP1. All right, and the heat of vaporization is given to me, and then this is going to be T2. All right, so now I need to just plug all these things in. So the natural log of, is it 1 over 2 or 2 over 1?
It's 1 over
2. So I'm going to say the natural log of 23.8 over x is what I'm looking for, is equal to, now here's an important part. You're going to take this 43.9 kilojoules per mole, and I'm going to type in 43,900 over 8.3145 times 1 over, I always get this mixed up, T2. Now T2 is 50 Celsius, and 50 Celsius in Kelvin is
298. Oh, no, sorry, it's 323.
323
sorry,
minus 1 over
298.
298. This, by the way, gets rid of the constant. The constant's not in this equation. And then you just plug this into your solver and you solve for it. I'm not going to teach you mathematically.
Yep.
I would, by the way, do natural log of
you use solver?
Oh, yeah, 23.8 divided by x, parentheses, minus 43,900 divide by 8.3145 times 1 divide by 323 minus 1 divide 298.
And I didn't use the solver, and I got the answer. It's 93.7.
And does that make sense? We went to a higher temperature, 50 degrees Celsius.
So we should have a higher pressure.
And our pressure was 23.8 at 25. So at 50, it should be a little higher. And actually, we could actually go back to that graph, by the way, I just had up a little bit ago. We were, 50 degrees Celsius? So at 50 degrees Celsius, water is saying it's 93. All right, I can live with that. That looks like about 93, doesn't it? Yeah. All right, so that's how you do those problems. Not terribly difficult. All right, now this is a graph that's important to understand as well. Okay, this particular graph, you have it in your handout, talks about, I have it.
This is the heated up, break it up graph.
The heated up, break it up graph. You saw this last year if you watched all those podcasts. But basically, down here I have ice. This is for water. And then we have melting ice,
ice and water are present right here. And this stage of the graph, I have just water. Here, water and steam. We just saw that a minute ago. And here we have steam. And this is just the heat versus the temperature. And this is at 273 Kelvin. This is 373 Kelvin, or 0 and 100 degrees Celsius. Okay, so this is an important graph, and there's two important things that we need to talk about. Okay, actually, let's talk about a couple things on this graph. First of all, if you are on the sloping portions of this graph, like right here, you're going to use the equation Q is equal to mc delta T. If you are on the flat portions of the graph, use the equation Q is equal to delta H, F in this case, times N for the moles. Okay, if you're in just the water stage, you'll do mc delta T. By the way, m stands for mass, c is the specific heat, and delta T is the change in temperature.
One other thing you want to watch out for is delta H is sometimes given in kilojoules per mole, sometimes given in kilojoules per
Actually,
gram.
on this graph, it's kilojoules or calories per gram.
Yeah, so
or
be
joules.
careful. Just watch your units. If it's per gram, do it times the mass. If it's per mole, do it times the moles.
That's exactly right. And this will be Q equals delta H, V for vaporization, times M or N, whichever unit you get. And the steam is mc delta T. You'll see, you've done these problems before.
Yeah,
so.
one other thing, the flat parts of the graph are always given in kilojoules, the delta H's are, and when you do Q equals mc delta T, your answer shows up in joules. And when you add them all together, if you're calculating like the total amount of energy, be careful to make sure your units are consistent.
All right, so now let's kind of review how to do this. So if I've got how many grams or how much energy is required to raise 7 grams of water from 50 to 100 degrees Celsius. Now if you go back to that graph, you're just going from 50 degrees Celsius, which is about right here, to 100 degrees Celsius. So the equation that applies is just the mc delta T. So you do Q equals mc delta T. And we're working with water. The C number, I'll explain that. This is 7 grams. C is the specific heat. And we've talked about this before, so I'm not going to belabor this. This is 4.18 joules per gram degree Celsius times the change in temperature from 50 degrees to 100 degrees. That is a 50-degree temperature change. And you get a total joulage of
1463.
1463 joules. Joulage, yeah.
That's kind of a neat word.
Yeah, or 1,500 joules. All right?
Yeah.
All right, not too bad. This next one is kind of a nasty problem, but you might expect to see this on an AP exam, so let's just
You also
do
might
it.
expect to see it in your homework.
Yeah, you will. We're going to go from negative 50 to 150 degrees Celsius. Now, you always start with this graph. Actually, let me just sketch it here. We're starting down here at negative 50 degrees Celsius, and we're going to go up to 150 degrees Celsius. So we have to take some ice, and we have to melt it. By the way, we're assuming that we live at sea level, and of course we don't, but oh well, too bad. 0 to 50, negative 50 to 0, and then I'm going to have to go from 0 to 0, and then I'm going to go from 0 to 100, and then 100 to 100, and then 100 to 150. So let's do that. All right, so the way I like to do this is I want to go from negative 50 degrees as a solid to 0 degrees as a solid. Now I'm going to use the equation Q is equal to mc delta T. And what was our mass in that problem?
I don't remember.
I don't either.
200 grams.
200 grams. So this will be 200 grams. Now this is going to be the specific heat of ice. Now these will be given in the problems.
That's
but
2.1 joules over gram degree Celsius.
2.1 joules per gram degree Celsius. And the change in temperature is 50 degrees. And that comes out to what, Mr. Sims?
21,000 joules.
21,000 joules. Now what I'd like to do right away at this stage is just call that 21 kilojoules. I think it's better to work in kilojoules. Then I'm going to go from 0 degrees as a solid to 0 degrees as a liquid. We're going to melt the ice.
Yep.
And you're going to use the equation delta HF times, is it an N or M?
I have the value in kilojoules per mole, so we're
So
going
we're
to
going to do N. Now, since we have to do sort of a pre-step here. If I have 200 grams, I need to convert that to moles. So
Yep.
there are 18 grams of water
Yep.
in 1 mole. If it's a different substance, of course, you use a different molar mass.
11.1.
This is 11.1 moles. So I'm going to use that over here. So this is going to be, now the heat of fusion would be given
6.02 kilojoules per
6.02
mole.
kilojoules per mole times 11.1 moles. Moles cancel, you get kilojoules. What do you get there, Mr. Sim?
We got 66.9.
66.9 kilojoules. Now something to make a note of, guys. That took 66 joules. This took 21 joules. Melting takes a lot of energy.
It does.
Breaking
And
up the
boiling's
bonds.
even worse.
Boiling's a lot worse, yeah. Then we go from 0 degrees as a liquid to 100 degrees as a liquid. And we'll use the equation mc delta T. I don't really need this one. I know it's going to be 200 grams. 220?
200.
200 times 4.18 joules per gram degree Celsius. I won't write that down. And then we're going to 100 degree change, so that's going to be 100 degrees. That's going to give us a big number.
Yeah, it's 83.6 kilojoules.
83,600 joules.
Yep.
That's what your calculator says, or 83.6 kilojoules. All right. All right. We aren't done yet. Then we have to go from 100 degrees as a liquid to 100 degrees as a gas.
Yep.
We'll use the equation delta H vaporization times N. The heat of vaporization of water is like 40
It's
something.
40.7
40.7
kilojoules per mole.
kilojoules per mole, and our moles were 11.1, just like where they were just a minute ago. So this is going to be like
452
452 kilojoules. Now that's huge
Kilojoules. That's a lot.
compared to the others. And lastly, this is a long problem, 100 degrees as a gas, as steam, to 150 degrees as a gas. So that'll be mc delta T, which will be 200 grams. Now the specific heat of steam is not the same as water.
2.0.
So it's 2.0 times 50 degrees. And this gives us how many joules?
60,000 joules.
60,000 joules, which of course is just 60 kilojoules. Now I just need to add up all my numbers. I have 452 plus 60 plus previous screen 83.6 plus 66.9 plus 21.
We get 683.5. 684.
Yeah, probably just go with 684 kilojoules. Okay? That was a long problem, but you should be expected to do that. Now, something that's intriguing to me in my brain about this whole deal is this 452 number. What is 452 divided by? 452 divided by 684 gives me 66%. 66% of your energy was used to boil the water.
Wow. It's a lot.
And that's because what you're doing is what's going on. Let's
Well,
kind of go back to that
breaking
graph.
up the hydrogen bonds. Those
Yeah.
are really strong.
You see, if you think of this, is you've got water molecules, and they're connected together, little Mickey Mouse guys. And when they're in steam, the water molecules are totally separated. Where here, they're kind of loosely connected by those hydrogen bonds. So breaking the hydrogen bonds takes a lot of energy.
It does.
So that's kind of the point of that. Okay. All right. Phase diagrams. State does not just depend upon temperature,
Nope.
but
Pressure.
pressure is also a factor. All right. Now you've seen these before. Phase diagram of water. Interesting thing about this, of course, is that let's just kind of diagram this. There's this thing called the triple point. What's that mean, Mr. Sam?
That's the point at which the solid, liquid, and gaseous phases all exist simultaneously. Only happens at one specific temperature and pressure.
That's exactly right. So they exist at the same time in temperature and pressure. So for water, which we have here, if it's 0.006 atmospheres
That's very low pressure.
and 0.01 degrees Celsius,
very, very cold.
the substance will be at a triple point. It's very, very cool. And so we can have ice. So if I'm at 1 atmosphere, which most people live close to 1 atmosphere, if you heat this up, this would be 0 degrees Celsius, and this would be 100 degrees Celsius. But like for where we live at 0.75 atmospheres. There won't be a whole lot of difference, but it's going to be here and here. Yeah. So it's going to melt at a slightly different temperature, although melting is pretty constant. It doesn't change a whole lot.
No.
Where the temperature change, or the boiling point, really does.
Yeah, interesting thing on this particular phase diagram, it shows us the actual scale.
Yeah.
You can see that line is almost straight up and down for the freezing point. It hardly changes at all.
Yeah, so yeah, exactly. But this is an important thing. So, but if I were to take, well, actually an interesting application to this. If I have an ice skater, right,
Uh-huh.
and they get on the ice, and they, so ice is a solid,
Yep.
right, okay, and then they have their blades hitting the ice.
So a lot of weight pushing down on a very small area is going to have a very
It's going to increase the
high
pressure. And what's
pressure.
it going to do? I didn't draw that very straightly, but very straight. And it's going to melt the ice.
It is.
And then actually, so when the skater is skating, they're actually not skating on ice. They're
No.
skating on a very thin sheet of
Water. That's why it's so stinking slippery.
Yes, indeed. In fact, we experienced
Kind of
that
like this morning driving into
morning.
work.
Yeah, we live in the mountains, and they had this sort of flash snowstorm, and I slipped off the highway. Actually, not off the highway. I slipped on the highway twice, almost hit this poor lady. Somehow I avoided her, or actually I think she avoided me. And I got on the side streets, and the snow was much better. Why is the snow better than a slick sheet of ice?
Because it's not compressed and it's not.
Yeah, it's not.
It's rough.
Yeah, you put a little bit of water on
Yeah.
top of some ice, and it's just.
I have studded snow tires. I got here just fine.
I have just tires. I have a 4x4. Interesting little diagram here. Of course, here. What is the top of Mount Everest? We were wondering what it was. I was speculating 400. I was way wrong.
I thought it might be low.
240. So the boiling point is 70. And Leadville, Colorado, not terribly far from where we live, in 510.
Okay.
Madison, Wisconsin. No, I don't believe that.
Yeah. 900 feet above sea level?
900 feet. 900 feet above sea level. I was looking for something
Yeah.
about 8,000 feet. Nothing in 8,000 feet land.
No, that's where we are. So we're somewhere between Mount Washington and Leadville.
Yeah, that's why our vapor pressure is
Right
like
around
or
570.
570 or whatever. Yeah, so that's just information to have. Oh, and one other thing is that we should talk about. Most phase diagrams, solid, liquid, gas ones, have more of a shape like this. This is the phase diagram of carbon dioxide, CO2. And what you notice here is that the slope of this line is more this direction, positive, where the slope for water is actually negative. Mm-hmm. The slope for water is negative. It's actually a very, very rare occurrence. The slope for most things are positive.
Mr. Bergman, what's the critical point?
You know, I just had that thought. We have not talked about the critical point.
We have not.
You know, but if you get above the critical point,
Yeah, very high pressure,
in terms
very
of
high temperature.
Actually, just to get above the temperature. If you get above the temperature, and so for carbon dioxide, it's not very high, really, but it's very high for liquid carbon dioxide, 30 degrees Celsius.
It's pretty substantial
It will
pressure.
always be a gas.
Yep.
It can never be anything but a gas. So it will be a gas above this. See, the molecular motion is so fast, the molecules are moving so fast with relation to each other, they will never connect to each other. So that's called the critical point. And it's a critical temperature is almost a better way to think of it. Because this whole thing, notice it's a straight line. Sometimes they call this the critical temperature instead of the critical point. All right. Any last comments, Mr. Sams, about the podcast?
We're
All right.
good.
I think we're good. We'll see
Alrighty.
you guys later. I can't talk today. I have problems. Bye-bye.